All right, so let's get started. So today we're going to continue our discussions on the flash memory, and we are going to discuss the core topics of the flash memory, that is the array architecture, NOR versus NAND. So here we are going to first discuss about this difference between the NOR versus NAND. So basically, when you have the floating gate transistor, you have to organize them into the array. And there are two ways to integrate into the array. So first, we have the NOR structure. So here, each transistor is organized more like in parallel, right? So then this is more like a NOR logic, because if you think about the Boolean logic, right, then when you have the NMOS transistor in parallel for the pull-down network, then it's more like a NOR. So that's why this is called a NOR flash array. So here then it's also similar to the DRAM, right? If you do not have that capacitor, then it's like the NOR array, right? So then basically the overlaps control the gates, the control gates, and then the bit NAND attached to the drain, and then the source NAND could be connected together as a common source. Okay. So in this case, the bit NAND and source NAND is kind of perpendicular. The other way to organize this flash memory array is a NAND structure. So here you see that we have the so-called NAND string, because here those floating gate transistor will be connected in series. It's like the NAND logic, right? The pull-down network in series, then it's like NAND. So here we call this is the one NAND string. And then at the top of the string, we have a regular transistor. This is not floating gate transistor. This is like a regular transistor as a string select. And also at the bottom, we have a ground select. So those two act as control transistor for the string. And then on the very top, then we connect the string to the bit NAND. And then at the very bottom, we have this common source. So this is a NOR versus NAND. Any questions here? So this is a schematic or netlist. And then let's look at the real layout. So in the NOR array, so what you can do is actually share the bit NAND contact. This is like a bit NAND contact between two transistors. Okay. So if you look at the layout, not layout, I mean the netlist, then it's like this, for example, this bit NAND contact shared between those two. Okay. This way you can save some area for the bit NAND contacts. So here we are looking at along one bit line. So essentially we are looking at along one bit line here. Okay. Then this is one bit line, and then we have multiple transistors, those floating gate transistors controlled by different word lamps, and they're in parallel, right? So that means each of them can be independently accessed once you give the word line and bit line address. So here, if you look at the cross-sectional view of the NOR flash, this is how it look like, right, from the side view. So here we have the floating control gate and the floating gate, and then we have the transistor here. So here, as I said, this bit NAND contact is shared between those two. And also here we have the real image from the microscope. So here from the top view, we are looking at the layout here. This is like the layout. So here the layout, if you look at this one, if you zoom in here, like the layout. So roughly speaking, it's like 10F square. Okay. So here the contact, since it's shared, so you have half F on each side. And then you have like some F between the contacts and the drain contact and the gate, like the spacer region, okay. And then the channel length, actually you may need to have like a 2F, because here the floating gate transistor will have to accommodate the large drain voltage for the NOR flash. We'll talk about that in the next. So the programming is done by the hot channel hot electron. If you recall the last lecture, we apply like large drain voltage like 5 or 6 volts. So here the channel length cannot be very small. Otherwise, you have the horizontal kind of breakdown from the drain to the source. So you have to make the channel a little bit large. So in total here, on the horizontal dimension, you have 5F. And then on the vertical dimension, of course, you have 2F because you have, 1F for the channel width, and then half F for the spacing on each side. So roughly speaking, we have like a 10F square for the NOR flash transistor. So any questions here? Okay, so then let's look at the operation schemes for the NOR flash cell. So here, first of all, for the erase, you can do the channel FN erase or source FN erase. So here, for example, here we have the source FN tunneling for the erase. So what you do here, for example, you apply like 12 volts to the source and then ground the gate, and then you will have this large electric field. So the electrons can flow out through the FN tunneling. This is for the erase. So if you look at the NOR array, then what you can do here is this source line, like 12 volts, and then all the cells attached to the source line will be erased together. Okay. So here then the gate is grounded, and then the drain could be floating. So open means floating, float. Okay. So here you have this FN tunneling. And this is generally kind of slow, right? You may need like hundreds of milliseconds for the erase. And then for the programming, so by the way, so if you look at the bias scheme in the table, so here we talk about the erase. So you have those bias voltage to the terminals, like the control gate, source, and the drain. And then the programming, okay, so here, very important. For the NOR flash, the programming is done by the channel hot electron programming. That means you apply 12 volts on the control gates and then 6 volt large drain voltage to have this large drain current. Of course, electron flows here. We discussed in last lecture, some of the electrons may get hot due to, the increased connecting energy. So they may jump over the barrier and then stored in the floating gates. So here you can do this by selecting individual bits in the array. So for example, here, this one is a selected cell. What you do is apply 12 volt to this word line, and then 6 volt to this bit line. and then ground the source. Okay. So then only this cell will have this programming condition. You can check the other cells. They, like the cell B, C, D, will not have the programming condition. So here again, in the table, we summarize the typical numbers. So here, for the unselected cell, what you need to do here, the bitman, ground, okay. So they will not have large currents, large drain currents. Therefore, they do not have the channel hot electron, okay. So then the programming, like a typical time, like a few microseconds, okay. And then the current could be as large as a few hundred microamp. So we still need to burn a lot of power, right? As I said earlier, the channel hot electron efficiency is not very high, right? You flow a lot of currents. Only a very small portion of the electrons will be injected to the floating gates. So after you do this programming, then you may have like a 3 to 5 volt VTH shift in the floating gate transistor here. So lastly, the read operation. Okay. So here, if you want to read out the data, then you can apply, like for example, 5 volts to the control gates. And then the difference, actually the read is similar to the programming in terms of the voltage you apply, but then you see the amplitude is lower, okay? For the read condition, so here, again, you want to read this cell, okay? Then the VLAN is turned on, but with only 5 volts instead of 12 volts. And then the bit line is also turned on, but here you only pass 1 volt to the bit line. So you do not have very large current. You have some regular, operation of the transistor, like 1 volt drain voltage. So you do not create too many hot electrons. You just want to sense what is the drain current in the nominal way. So here then, depending on the threshold voltage, you may read out the currents. If the is erased, then the threshold voltage may be very high. Then you won't, read any current. So the threshold voltage may be even higher than your 5 volts gate voltage. So the read is pretty fast actually in the low flash. Okay. So it's like a regular transistor, and then you will have, if you have like 1 volt, you may pass like tens of microamp. Therefore, the read speed could be as fast as like 50 nanoseconds for the read. So here you see that for the program and erase, you can select individual cells. Okay. That means random access. Okay. Given by the address, right? So then you can locate this cell and read out this cell. But for the erase, in general, you have to erase the entire array, or at least the cells that share the common source net. Okay. So any questions on this one?
After the read is done, does it happen like VRAM where it uses its memory and they have to reprogram?
No. So in general, here the read is like non-destructive. So you won't lose the states. Okay. This is non-volatile memory, right? So, but of course, there are some concerns, and we'll discuss that in the next slide. That is the disturb. Okay. Especially during the program, you will have the disturb concern. So what is disturb? Disturb means you are going to program one cell, but then the adjacent cells may also be affected. That means adjacent cells threshold voltage may also change a little bit, and we call this behavior like disturb. Okay. So for example, let's look at this again. For the program we show here, right? So we said that program, this is a selected cell. But here you look at the cell, let's say cell B. So cell B share the same word line as the cell A. So that means here you have 12 volts on the gate. But then the drain is 0 instead of 6 volts. So then you do not have large current here. The drain current is small, but still the gate voltage is kind of large, like 12 volts. So you may have some internally, right, of the electrons. So even though this is not large enough to, especially under a short pulse, because here the program pulse is like, tens of microsecond. So here, then, of course, if you boost this to like 15 volts or even 20 volts, then you have a lot of F internally from the cell B. But under the condition like 12 volts is somewhere in the middle, then the turn-on rate is low, but still, if you keep doing, let's say, the programming of the cell A, then the cell B, after cumulative, program disturb, then you get more and more electrons trapped into the floating gate. So the threshold voltage of the cell B will also shift. So that is the potential problem, okay? And also for the cell C, here, even though it's unselected, so the word line is 0, but here the drain current, drain voltage is large. So here still you may have certain probability to have this, like a source, or in this case, drain F internally to remove some electrons from the floating gates. So the probability is lower than the regular program erase operation. But if you keep doing that, then over time, you may see some shift of the threshold voltage. So this is a disturbed issue for the NOR flash. So any questions here? So basically the cell A is called selected cell, and sometimes we call the cell B and the C. Basically, when you share the same word line or share the same bit line, they will be so-called half-selected cell because they're half-selected, they share the same word line or bit line. Only the cell D is totally unselected, right? Cell D, because, yeah, it's orthogonal to this one. So cell D, you do not have any voltage applied. So then cell D is unselected. So here we only show 2 by 2, like a mini array. But you can imagine, have a larger array than along the same word line or along the same bit line. You have many of those half-selected cells. Okay, then the law array is organized into this word line and bit lines. And in practice, actually, those two cells may share the same bit line contact for the physical layouts. But from the netlist point of view, they are equivalent. Okay, you draw this way or you draw the other way. From the netlist point of view, they have the same logic function. But anyway, here is a typical organization of the NOR flash memory, and it's organized into many of those segments, and basically one row, they call it one segment. And here, in this particular example, every time they're going to read out one word, which means 16 bits and 2 bytes. And then along one row, they may have 64 times 4 words. So in total, basically one row, they have like a 512 bytes, okay? And then here, you have many rows. And then one bank, you may have here like 64 kilobytes. This is relatively small in the older designs. So this is the organization of the NOR array. And then let's talk about the land, because we are going to focus on the land in most of our discussions, right? So here, the land will also show the schematic and also the cross-sectional view and also the real images under the microscope. So here we show one string, okay, one string. That means we show one string like this. And then one string, you know, at the top, we have the string select. That is this one, this string select transistor. And then after that, then it's attached to the bitman, attached to this bitman through the contact via bitman contacts. And then we have a string of those transistors in series. Right? We have many of those transistors in series. Okay. And then at the end of this, we have this string select or the ground select. Okay. So I would say that those are the floating gate transistor. We should have double line here. But at the end is a regular transistor. Okay, so if you look at one cell along the string, here you have this kind of layout. So the key is that the floating gate transistor between those two, they're in series. So you do not have the source, even though this is source and drain of the transistor, right? And you have the gate. This is top view layout. So the key here is there's no contact to the source or drain. You have those transistors. They are in series. But here you do not need to make a contact to connect to the bitline or something. Therefore, you save the contact area. Here you do not have the contact. If you make a contact, then you have to, you know, allow some space between the contacts via. But in this case, you do not have the contact. Okay, you do not have the contact. So that means here you can be very tight in terms of the spacing. So in that case, there's no contact here. So here, what you need is just 1F for the gate length and half F because you share this spacing, right? Half F. So you have 2F horizontally and also 2F vertically. So essentially you have one wire line and one bit line. You know, the wire will consume 1F and then the spacing between wires will consume another F. So that's why you got this 4F square cell size. This is in the 2D NAND. Later we'll talk about 3D, but here, as I said, in the 2D, let's say planar transistor technology, NAND is the smallest, right? Because you do not have the contact in between. So this is a minimal, theoretically minimal cell size. So any questions here? Yeah. So one string, I mean, correspond to one bit line. I mean, within one subarray. Yeah. Okay, so typically how many floating gate transistors share the string? So in general, in the 2D NAND, it's about like 64 transistors share the. So here, of course, in this schematic, we only show like 7 or that's 8, whereas 0 to whereas 7, just as an example, right? But in the real designs, you may have like 64 from whereas 0 to whereas 63, okay? And then you have the string select and then the for the ground select and string select at the end of the string. So here then, typically this is how the NAND flash is organized into the array. So you may have like still 8 bits, 8 streams, like as 1 byte, okay? And then here the number of streams within one block is very large. So you may have here like 2 kilobyte bitmaps or 2 kilobyte streams per page. So here the term page actually means one row or one word line. It's the same thing. Okay, in the NAND flash, it's the same concept. Or one page, they call one page. One page is one row or one word line. And one word line may have here, in this case, 2 kilobytes. So here, 2 kilobytes. That means 2 kilo times 8. 2 kilo times 8. Number of rows. Oh, sorry, number of columns. That means number of BLs for one word line. That is one page. And how many pages? How many word lines? As I said earlier, typically like 64 word lines or 64 pages as one block. So if you think about one block here, okay, this one block is a very rectangle block because vertically you only have 64 word lines or rows, and then horizontally you will have here 2 kilobytes. That means 2k times 8 number of bit lengths. Okay, 64 word lengths. So it's very, very like very rectangle, right? It's not like SRAM. You have like a 32 by 32 or 128 by 128, like a square. So here, this is a very, very rectangle. Of course, in the real product, you may have additional like parity bits for the ECC for the error correction control. And here, you may have many of those blocks, okay, for one chip. So in this example, this 2 gigabits, which is like an older generation. So actually, you may have like 2,000 blocks, okay. So in total, you have 2 gigabits per chip. So here, we have some like timing information. Like the erase is by the block. You have to erase entire block, this entire block. And then it's about like 500 microseconds. And then here the read is also slow, okay. If you initially load a page, you give a random address and then go to that particular word line, read that word line. It may take like 20 microseconds, 25 microseconds. So this is the general feature of the NAND. We'll talk about more details in the following slide. But overall, you need to understand this is a very rectangle block. So here's another view of this very rectangle block. As I said, for example, here you may have 64 word lines for one string. And then you have the string select, the ground select, and then the common source none, and then bit none. And here, in the previous example, is 2 kilobytes. That's an older generation. But in modern, recent generations, still here we talk about 2D NAND. Okay, 3D will be totally different. But let's say in the 2D, you may have as much as 16 kilobytes. Okay, along this horizontal direction. So it's even more, rectangle. So again, we have to emphasize the read and the program operation will be performed per page. Okay. Once you read, you're going to read the entire row, or when you program, you're going to program the entire row. Like this green dash box, you're going to read out those together. And then when you do the erase, you will erase the entire block, which is this red dash box. Okay. This means program here, read here, but erase like the entire block.
block and array mean the same thing?
Yes. So in this case, the block means one subarray. Yes. Or it's like one mat in DRAM. But in different memories, people just use different names, but it's the same concept. The minimal unit size of the array. Okay, so then let's talk about the NAND operation schemes. And the erase, as I said, will be erased by the block. You can erase one single block, you can erase multiple blocks together, but the minimal unit to erase is the entire block. Actually, it's large, right? Because here, for example, even in this 2D NAND, you have like 64 times, 16 kilobytes. That means already you erase like one block is like megabytes. So here, the erase actually is straightforward. We're going to use a channel FN tunneling, right? So you need to apply large voltage to the substrate or the body. And then here, for example, you ground the gate, sorry. Actually, this is something a little bit tricky here. So you need to not ground here. Yeah, you can ground here. That is, actually you should float here. Okay, you float. So here, so basically you have to apply large voltage to the substrate and then ground the gate. Because the source and drain actually will be float in this case. So you look at this string, right? So you float this like string select, ground select, and then bitline. So what you have is that like 20 volt applied to this, because the substrate will be shared, right? All the transistors share the same substrate. You have this 20 volts, and then you have large voltage across the channel, and then the gates. Then the electrons will be coming out. Then you erase all the cells together. And then the erase would take up to like millisecond. At least the 500 microsecond to a few milliseconds. So let's talk about the program. This is the tricky part. I need you to pay special attention to the following discussions. This is one of the most difficult parts in the NAND lecture, or even in our entire memory class. This is the most tricky part. So let's look at the program condition. It's not very straightforward. As I said, so the program, you have to select this one page, for example, this page. But you only program some of those cells, right? Depending on your data pattern, because after you erase means actually you are going to write all the data. Let's say erase means you get all the electrons out. Then the threshold voltage will be low. And then that means all the data will be 1. So a fresh block, all the data is 1. And then now you need to write the new data in. You select a certain row or certain page, and then you need to flip some of the data from 1 to 0, depending on your new data pattern, right? So that means some of the cells need to be programmed. Some of them you should keep the ones. So you will have this selected cell, and then in this example here, this one is a selected cell, and then the cell B here will be unselected or half selected. So we have to make sure the cell B will not be programmed. So with this, we call this as inhibit. So that's why when we talk about the program, we need to also talk about the inhibit, okay? Because some of the cells you need to program, some of the cells you need to be inhibited from program, okay? So let's look at how we do this for the program cell. Let's say this one. So what we need to do first is to turn on this, because we are going to, of course, select this screen. So you are going to turn on the, let's say, the screen select here, like a 10 volts. And then this needs to be grounded, okay? Then you allow this ground from the bit line to be passed. Oh, by the way, so here the ground select need to be 0. So in that in this way, the string actually, the entire string is like a floating. So the essential goal is to deliver the voltage. Is like, if you look at single transistor, okay, the source side is floating, okay, right? Because here, if this is ground, then this is like a floating. So for a transistor in this floating condition, this is very important. You need to deliver this voltage, I mean, to the source side. Floating means this source side voltage can be any value, depending on what? Depending on how you apply the voltage to the gate and the drain. So what would be the source voltage here in this condition? So the source voltage will be the minimal of VG minus VT, the threshold, compared to the VD. Okay. So if the VGS, let's say if the gate voltage is very large, and then after the VTH drop is still very large, then the drain voltage could be fully transferred or delivered to the source side in the pass gate condition. Okay, recall your device physics. So that's why if the drain voltage is smaller, drain voltage will become the limiting factor to determine what is the source voltage. So that's why we have this mean value. Minimal, let's say those two, you choose the smaller one. So if the drain voltage is smaller than VG minus VT threshold voltage, then the source side will be the same as the drain voltage, fully transferred. But if the gate voltage is kind of small, especially after minus VT, then if this is small, then the drain voltage cannot be fully transferred. You have this VTH drop problem in the pass gate logic. So then the source side will be limited by the gate voltage minus VT. Okay. So if you use this rule, you can look at what will happen here. So for the program cell here, you want the 0 voltage ground to be fully transferred to the channel. The reason is that you need to create like 20 volts programming voltage to the gate, and then you want the channel to be ground. So essentially you want the cell in this kind of condition, that channel is 0, and the gate is like 20 volts. So you have this F internally. So in order for you to do that, you have to pass, because this 0 voltage needs to go through here. So that means you have to pass those, this is the transistors along this, string needs to be in the pass condition. So here, then we need to pass this 0. So here, for example, we apply 10 volt here, or like 9 volt here, or 10 volt here, then this could be fully transferred, okay? I will talk about why you need 10 volt here. If you only consider the, let's say, this selected bit line, you don't need 10 volts, because here this drain voltage is very small. Actually, it's ground. So you can only just turn on a little bit. As long as this is larger than the threshold voltage, you can transfer the 0 volts. The reason you need to apply like 10 volts is because of this unselected cell. And I mean the second string here. You need to inhibit. That's the reason. So so here we have to consider this together, okay? So for the cell B, what will happen? Cell B will share the same wire line as the selected cell. That means cell B, you have 20 volt here. this is dangerous. Okay, if the channel potential is not high, then the voltage across that, the cell B will also be programmed. But you don't want to program cell B, right? So then you need to find a way to increase the channel potential of the cell B. Therefore, this voltage drop across the cell B is not high. For example, here, if you can increase the channel potential to 8 volts, then only 12 volts across that compared to here 20 volts. Then the cell B will be inhibited from the programming. Of course, it's under disturbed condition, but it's not 12 volts is not 20 volts, so it's inhibited. So how do you make sure this is like 12 volts? So the tricky part is here. The V inhibits, you need to apply, for example, here, the V inhibits, you need to apply, let's say, maybe, let's say for V inhibits, you apply 9 volts, for example. So this 9 volts, that's why here, this pass gate condition, you need like 10 volt here. Because typically, let's say your threshold voltage is like 1 volt. 10 minus 1 is 9 volt, and here you have 9 volt. Record this pass condition, so you can transfer this 9 volt to the source of this transistor. And also you need to turn on all the rest of those transistor along the string, right? So here this gate voltage, that is the V pass W, the V pass for the right condition. You need to also turn on this one. So that's why here this one you need to apply like 9 volt or 10 volt to transfer this 9 volts. Or maybe you have like 1 volt VTH drop. But anyway, so here when you transfer this, maybe until here, the channel is like 8 volts also. So the reason you need to have this like a large voltage, like 9 volt, 10 volt for this pass, V pass, is because you have to transfer the V inhibits to the cell B to raise the channel potential of the cell B. So any questions here? So here, I think you can read the text on the conditions after the class. I think we write down what need to be applied and the reason behind that. So actually, this was not the modern way to do this program inhibits. This was used long time back. There are some drawbacks in this kind of design. This is called the channel inhibition scheme. Channel inhibition. So the drawback, as you can tell, is that you apply kind of large voltage, like 10 volts, to this string select transistor. Of course, then there'll be like reliability concerns because those are not floating gate transistor. Those are regular transistor, right? This voltage is large. Because floating gate, you can sustain high voltage because the floating gate additional gate and the thickness is high, and yeah, the gates, those oxide thickness is high, so you can sustain high voltage. And also here, when you apply like this large voltage, you have to spend a lot of dynamic power consumption because you have to toggle those rows with high voltage, right? Then when you charge those overline bitline, you need to have pay for the CV square energy, because when you charge up, right, you need to have the CV square. So then
the selected line is way further, then the inhibit voltage has to be much higher, right? Because it will have a lot of VTH drops. So the selected line, instead of being at the third row, if it is like say 10th row, then the voltage has to be much higher. Is that an issue?
I don't get your question.
The you got 8 volt, right?
Yes. Yes.
If this was way further in the bottom.
You mean what if the inhibition voltage is higher than 10 volts?
Might be more than 10 volt, right? If say the cell in the last row was.
Oh, in the last row, okay, you mean there's additional like IR drop. So as long as you can fully transfer those, you fully turn on those, this 9 volts, whatever you apply here could be, transferred to the along entire string. Okay, no problem. Because there's no IR drop actually, because here is no no current flow, because at the end of the column is off. So that's why it's not in the DC current mode. If you have current along the string, yes, after you pass in each transistor, you have IR drop, then the voltage will become smaller and smaller. But here there's no real static current, right? It's just this condition, as I said. So you fully transfer. Okay. So here then let's talk about some common way. This is most standard way people use. I mean, and this is I think a standard way for the industry, at least for the 2D NAND. This is called channel self-boost scheme. Okay. So similarly, the goal is the same. We want to program this cell, selected cell, and then want to inhibit the cell that share the same VLAN. So instead of applying like 10 volts to the string select here, we just want to apply like 3 volts to this VCC, the common collector voltage. So we want to apply 3 volts instead of 10 volts to the inhibition and also the string select line. So here we have to play with the timing a little bit. So the idea is that here, okay, let's apply 3 volts to the inhibition. I mean, for the selected string, this will be the same, no difference. The only difference is here on this one. So 3 volt here and 3 volt here, okay. And then this is a timing, okay. 3 volts, 3 volts. And then for all the VLANs, you are going to first move the voltage to the V pass condition, which is like 10 volts. And then the reason here, this 3 volts, because here you have 10 volts. So this transistor actually is off. This transistor is off, okay. Because here the VGS is 0, right? You have the gate VCC and here. Because here on the other side, this is higher voltage. So this becomes a drain, this becomes a source. So this is like VGS. So the key is that we want to even float from the top. Previously, we do not float from the top, we only float from the bottom. So bottom is float, this for sure. But here, for this one, we want to float even from the top. So once this is float, okay, after you first reach this V pass condition, then we float the top. And then for the selected VLAN, we are going to jump to the programming condition, which is like 20 volts. So then for this selected bitline, because bitline is for selected one, this is always 0, so you still have this 20 volt across that. You program that. This is the same as before. So here, but what will happen for this unselected bitline? There will be a coupling, because now both sides is floating. So the channel potential can be any value, depending on what? On the coupling from this V program to the channel. Or if you look at the capacitive model we show on the right, because it's all floating, then it's just a bunch of capacitors essentially. So what we show here is this is a string, okay, and then we have all the capacitance, okay, because this is floating, as I said, both sides floating. So here, for each of those transistors, you have the gate capacitance, right? For the string select, and then for the cell, you have all the gate capacitance. And then here, the channel is coupled to the substrate, right, through the C substrate. So here, this channel voltage can be any value because this is floating, right? And this channel is shared. This channel is shared. The string is shared. So here, the voltage, you can, use this simple capacitor model and calculate what is the voltage given. Let's say you apply the voltage VCC to here, ground here, and for the pass condition, then you have the V pass. The only one you apply high voltage is V program, right? You have all those capacitors. It's like what we showed in the last lecture on this simple, let's say, gate coupling, right? Problem for gate coupling ratio, if you recall that. So I will skip the derivation. Basically, you can solve what is the V channel here based on the voltages, right? It's just a divider with different voltages. So if you do that, then that is the equation. So the channel voltage is a division of the cell cap versus this ratio, of course, depending on how many cells, and then V pass. Okay. So basically, this one, and you will have the charge redistribution by the V pass voltages, and then the V programming. So this V channel will be higher depending on those voltages. Okay. Of course, you can plug in some numbers and calculate. I believe that your homework may have some questions on this. So, but anyway, so the point is that the channel potential is self-boosted to a higher value. That prevents the programming. So here, this is not the best way because the V channel voltage actually might not be very high because mostly this will be determined by the V pass, right? If you need to do the first order calculation here, this will be divided by N. This is higher voltage, right? Let's say this 10 volts, this 20 volts. Of course, you want this V channel higher, the better. But here, if you look at this 20 volt is, if you assume those are on the same order, okay, maybe just on the same order, then this 20 volt will be divided by N. N is number of word lengths you shared, like 64. And then here, this one is almost the same. So mostly it's more like V pass condition. Of course, here you may have the ratio like half. Just to the first order, of course, depending on the exact value. So you see that mostly this will be determined by the first term. If this C cell if C cell is the same as C sub, then this is just half. And then this is like 10 volts. And then you only get like 5 volts. To the first order, okay? To the first order. Because this second one, 20 volt, is diminished, right? Divided by 64, then it's almost nothing, okay? So then the efficiency is not that good. So you can improve this a little bit. So here, this is the improved version, like channel self-boost scheme, the variance. So here you can do the Snowcode self-boost. What you can do here is, for example, here, we used to have this V pass for all those transistors along the string. But let's do that, let's say with 0 adjacent to this selected row. So if you do 0 on this, let's say the upper and lower, that will basically isolate. You will make the float condition only to this cell. Previously, we make the float condition, but recall, from the very top of the string to the very bottom of the string, the channel is shared, okay? So that's why here this voltage potential is not that high because charge is shared across the entire string. But here, if you boost locally, you cut off this one, then this V programming will be only coupled to this cell, right? If you look at this kind of a schematic, then basically you cut off here and cut off here. This V channel is only a simple voltage divider by this one. And then you can get the equation very easily, like this one. Right, you only have two capacitors, then it's just a divider like this. And then here, if they're the same, as I said, then it's just easily you get like 10 volts. Right.
Have like a higher channel voltage to be negative more.
The goal is to have higher channel voltage to, to have the inhibition. Okay, so then does this cause some trouble? Okay, if you do this one, the reason is that here, if you apply 0 volts, how about this selected string? You will cut off this one as well. Then this 0 may not be delivered to here. Then you cannot program this one very well. So as a trade-off, then you can do this asymmetric self-boost. That means above this, let's say, all those cells above, you apply V-pass. All the cells, just ground the cell below what you are going to program. So you are going to share, let's say, then this all of those together instead of cut off the let's say. You can cut somewhere in the middle. I mean, float. So you reduce the sharing. Then if you do that, then you get this equation, and just depending on how many, let's say, of course, this will be different. The potential will be different depending on the location where the M is. So you record this in total is N, and then the selected cell is M. Then you will have this equation for that. So basically, you choose where to cut. So any questions? I know it's a little bit tricky. As I said, this is the most difficult part in this lecture. But as you understand the principle, as I said, right, you need to first understand the pass condition of the NMOS transistor. Second, think about what is your goal. Your goal is to program the selected cell and inhibit the cell that is along the same line. What you need to do is to raise the channel potential of that inhibited cell. Okay. So then let's move on to the rate condition. So the rate condition, this is a typical like a IDVG of the floating gate transistor cell. Let's say in the erased state, the VTH actually is negative. And then in the program state, the VTH, for example, could be positive 2 volts. So you have like 4 volt memory window in between. So what you can do is to read actually somewhere in the middle. If you have your read voltage somewhere in the middle, then you can detect current versus no current or very small currents. So here, then again, you are going to read row by row. So here for this selected row, you need to apply the read voltage. In this case, actually the read voltage 0 volt is good enough, right? So this one, like 0 volts. But the problem is that here for the bitline, now you don't need to have very large bitline, like 0.3 volt, 0.5 volts, good enough. You just want to, have some current flow. So, but then the tricky part is that you have to, again, transfer this bitline voltage to the here, right? So here, then those transistors on the top. By the way, here you cannot ground this ground select. You need to allow it to pass. Okay, you need to allow the current to flow. Otherwise, it's floating. then you don't read out anything. So you need to allow the current to flow. And then the thing is that you have to make sure this bit voltage is transferred to this selected cell. Okay. That means here for the other cells, they need to be in the pass condition. And here we call it V pass R, R for read. This is different from V pass W, which is the programming. So here, what is the V pass R voltage? Any idea? How do you design V pass R if, let's say, I should give you this kind of IDVG curve for this technology? Then what should be your V pass R? Any idea? Somewhere here, here, here. Which one? Which one should be your V pass R? I already said VR is here, the read one. This one is 0 volts. Now I'm asking where is the V pass R to be applied to other rows? Should be here, okay? Somewhere here. So for example, you choose 4 volts in this case. So the reason is that because for the other cells, you don't know what is their data or states. You have to assume they are in the program state, that means 0. You need to pass even under the 0 condition. So that's why here you need to turn on those transistors, fully turn on. Even if they are in the program state. That means this V pass needs to be higher than the threshold voltage of your program state. Sufficiently higher than that to allow this transistor to be fully turned on, even you store the data 0. Right. Of course, if you store data 1, then it's an easy kill. You can turn on it easily, but you don't know, right? Beforehand, you don't know. Okay. So any questions here? As I said, tricky for the land. So then the land is based on some high voltage operation, right? So that means the peripheral circuits need to generate this high voltage. Typically, what you will have is like from your I/O, you have like a regular like I/O voltage, like 2 volts, 3 volts. Then those high voltage will be generated on chip, okay, through some charge pump circuitry. So you boost like your voltage by stacking capacitors and so on. So you generate a very high voltage, like 20 or 30 volts. And then, for example, here, this 20 volts, you need to apply to the, for example, the selected cell for the programming. And then, like this 8 volts, you need to apply to this V pass, right, V pass W, right, for those unselected cells. So some of the cells you have like 20 volts, some of them you have 8 volts. And then for the VLAN, like the driver for the VLAN, this needs to be controlled by the address, which one to be turned on, right? So that means from after the decoder of decoding your address, you need to raise up the voltage through the level shifter to allow like 30 volts to fully transfer, the voltage to the VLAN. So there are a lot of like high voltage circuitry on the NAND flash peripheral circuits. So any questions? Then let's talk about the NAND versus NOR. So here, historically, NAND flash, because higher density, right? Each cell like 4F square, NOR flash like 10F square. So NAND flash is higher density, so that's why it's better to store your massive data into the NAND flash. But NAND flash is slower than the NOR flash, especially the read performance. So for some critical programs, for example, you boot up the system, you store some code, the boot up code of your system, then those code are generally stored in the NOR flash. But the NAND flash is dominating the market right now. Many of those, operations now can be done by the NAND flash. So the NOR market is kind of small, okay? So the overall comparison between the NAND versus NOR summarized here. So here we already set the cell size, right? So for the 2D SLC single level cell, then you have 4F square. And the multi-level cell, then NOR flash, you can do multi-level, and then NAND flash, you can even do 4 bit per cell. And we'll talk about that in the next lecture. So here, then, what's the difference? The key difference is NOR flash, you can do the random access. You can give the row address and column address and read out that data. But NAND flash, you will not be able to do that. I will talk about the NAND flash operation in the next few slides. So it's not very friendly actually to software. So I will talk about that in the next few slides. So it's not random access, okay? And then the programming condition, mechanism is also different. NOR flash, channel hot electron, NAND flash, FN tunneling, right? So here the key difference, the rate latency is a key difference, okay? So here the red bandwidth, if you look at bandwidth, actually NAND flash is faster in terms of bandwidth because it operates on large page. You can do them simultaneously. So from the bandwidth point of view, it's actually okay. But the latency to get the data is very slow, okay? Even though every time you can get a lot of data, but then you have to wait for this latency, like a microsecond. So then, yeah, so we'll talk about the reliability issues later. But the key difference is the density versus the random access rate latency. So here, that's why for the high density, large capacity, like a storage, NAND dominates in terms of tens of gigabyte, hundreds of gigabytes, NAND flash. This is through the 2D NAND to the 3D NAND. Even today, you can get 1 terabit per chip by the 3D NAND. And NOR flash remains on single-digit gigabyte level. Okay. So here, if you think about the write performance, right, as I said before, NOR flash, you rely on this channel hot electron, then the efficiency is very low. Only a very small portion of the electrons get injected. And then the FN tunneling in the NAND is more, efficient. So power consumption-wise, for the write operation, then NOR flash is much higher because you have to flow the large currents. So then, from the layout point of view, actually, this is another way to look at the layout. Why the NAND is higher density? Because NOR, actually, you can also do this along the 1-bit line. You have this NOR. The key reason, because NOR, you have to have the parallel access to individual transistor for the random access. So that's why you need to have the contact to the bit line. At least every 2 of them need to share 1 bit line contact. So that's why it's not as dense as the flash. I mean the NAND flash. NAND flash, as I said, you don't need the contact in between. You only need the contact at the end of the string. You share the contact area across like 64 cells, so you can ignore that. Also, because here you have parallel access to each individual NOR cell, so you can read it fast. Why? Because you hear this transistor is attached to the bit line directly. Each of them is attached to the bit line directly, so you can read it fast because the RC delay along this path is small. But for the NAND, it's very different. So if you read this cell, the current needs to pass, many cells to reach to the bit line. So each transistor's channel resistance will add up. That's why NAND is slow. Okay. All right. So then, any questions? We have 5 minutes. So let me finish this one. So the NAND flash, from the system point of view, we have to use this FTL, flash transition layer, to basically manage the mapping from your logic space to the physical layer. So here, this FTL is some controller integrated on your NAND chip. Actually, maybe on the board. I mean, it's a separate, maybe a separate controller on your NAND board. So here, what is important is that when you have the logic layer, you have many of page data, right? Each page, let's say 16 kilobyte data. Then in the logic space, they may be continuous, okay, from your logic, from your software point of view. Then you assume this data. For example, your one image, one picture, you have, let's say 1 megabyte pixel values, right? So you save that to your SSD. So from the software point of view, they're continuous, right? The same image. But when you store that to the flash, maybe they are discontinuous, okay? They are stored in different locations, okay? So you need some translation from the logic layer to the physical layer to handle the data, because there are many invalid or garbage in the physical layer. We'll talk about that in the next slide to give you some examples to understand this better. So the reason is that because the NAND flash, as I said, when you write or read, it's page by page, one row by one row. But when you erase, then it's entire block, okay? So once you erase, the entire block data, become one, right, as I said. So the goal to write the data in or program the data in to flip some ones to zero. So initially you have all of them to be one. Now you want to write the new data after you take the picture, right? You save the picture image, then some of them become zero, okay? So there's a right pointer, okay, to the physical layer. So at this moment, this pointer is pointing to some page. You are going to do the operation there. You cannot move the pointer anywhere as you wish. So the physical pointer is there. Okay, you can only move the pointer one by one. So then here, for example, now at this moment, you want to write this new data to the logic block. In this case, 2 kilobyte data. Okay. So in the logic address, you have, let's say you use 2K, represent that there's a 2 kilobyte data. So you need to map that to the physical layer. Okay. So here, because at this moment, your physical layer pointer is pointing to the block 2, page number 63. Okay. So that means actually it's here. Let's say this is block 2. It's pointing to this last row. And before that is all one. Okay, it's all one. Now you write the new data in. So whatever data you have here, then you have the inhibition, whatever, then you do. Then you flip some of them to be 0. Okay. So you need to update this mapping table. So you need to remember now in the logic space, this 2K data now is mapped to the block 2, the last page, 63. Okay. And also there's a information table you have to update. So because previously this logic block 2K is mapped to the, let's say, block 0. Now you move to the block 1. So you need to delete block 0. Valid page count reduced by 1. And then here, your block 2, you increase the valid page count. So the data you store previously in the logic block, this data stored in this block 0. You still have something there. Okay. The old data of this logic address is still there, but you no longer need it. So this becomes invalid. Okay. You don't throw it away physically. It's still there, but there's no mapping to the logic space. Okay. So you keep doing this new data, and let's say you have another new data, and then you write the new row. Okay, that is fine. You keep doing that. You update the table. So let's talk about the erase. So when you erase, as I said, you have to, because as I said, in this block, some of the pages are valid, right? Valid. Because some of them you already move the point logic address to another location. So this becomes invalid. This becomes a garbage. Okay. So here, when you erase this block, because you are going to erase all of them to be 1, but still there are some valid page. What you need to do is to, collect the valid page, because now your pointer is pointing to some new block. Before you erase this old block 2, then you need to read out the valid pages and write them here to the whatever your pointer is right now. After you do the movement, then you erase this entire block. So when do you decide to erase the block? When this garbage portion becomes high enough, right? For example, 90% of this block is invalid. Then you want to, refresh that. So you decide to, okay, move the rest 10% to the new location, and then erase this one. So after erase, you need to count how many erase cycles this block has gone through, because that relates to the endurance management later. We'll talk about wear leveling. So, but anyway, so it's not of, management ongoing here, because you cannot move this pointer randomly. You have to go one by one. Okay. So then, as I said, you erase this entire block now. All right. So I think time is up. So any questions before we end? Today's lecture, is, kind of tricky. I wish you could, review after class. All right. Thank you.